There is an image of the solar system almost everyone recognizes. The Sun sits near one edge. 8 planets follow in a neat line, each large enough to display its color, rings, clouds, or familiar surface. The spaces between them seem significant, but manageable. At a glance, the entire planetary system appears like a family gathered for a portrait. It is a useful picture. It helps us remember the order of the worlds. But as a map, it cannot be true. To see why, impose one simple rule. Every object and every distance must be reduced by exactly the same amount. Nothing can be enlarged for visibility. Nothing can be pulled inward to fit the frame. If the planets disappear, they must remain invisible. If the model becomes too large, the frame must expand. Imagine shrinking the Sun until it becomes a ball 14 centimeters wide, small enough to hold between 2 hands. On that same scale, Earth is no longer a blue marble. It is roughly the size of a small grain, only about 1 millimeter across, and it cannot sit beside the model Sun. It must be placed about 15 meters away. From the Sun, Earth would be difficult to notice. From Earth, the Sun would still dominate the sky of the model. Between them would lie almost nothing that the eye could use as a marker. The distance would not look dramatic, because distance itself has no visible surface. It would appear as an ordinary stretch of air, yet that blank interval would contain almost all of the model. Now try to place the whole solar system inside one image. If the 14-centimeter Sun remains visible, Neptune belongs roughly 450 meters away. The model would extend across several city blocks. Neptune itself would be only a few millimeters wide. A camera positioned far enough back to include both the Sun and Neptune would reduce the planets to tiny marks. On a phone screen, some would vanish completely. If the camera moves closer so that the planets can be seen, the real distances no longer fit. The editor must enlarge the worlds, compress the gaps, or use both tricks at once. That is why the familiar planetary lineup looks crowded. It is not attempting to show location. It is arranging objects for comparison. This is not a failure of illustration. A diagram is allowed to simplify reality when its purpose is clear. A subway map distorts geography so passengers can understand connections. A portrait of the planets distorts space so viewers can compare appearance and order. The mistake begins only when the mind quietly stores that portrait as a picture of the actual solar system. The distortion is enormous because 2 very different scales must compete for the same frame. Planetary diameters are large by human standards, but orbital distances are vastly larger. Preserve the diameters, and the gaps escape the page. Preserve the gaps, and the worlds become points. No clever choice of camera can remove that mathematical conflict from a linear image. Even the word empty requires care. The space between planets is not absolute nothingness. It contains sunlight, magnetic fields, thin plasma, dust, radiation, and countless small bodies. Yet, compared with the dimensions of the major planets, the system is extraordinarily sparse. Most of its volume is not occupied by the round worlds shown in the family portrait. The planets are islands, and the distances are the ocean. But even that image can mislead. An ocean provides waves, weather, landmarks, and a continuous surface. Interplanetary space offers no road and no visible boundary telling a traveler how much has been crossed. A spacecraft can move for millions of kilometers while its destination remains little more than a point against darkness. There is another way to expose the missing distance. Instead of asking how many kilometers separate two places, ask how long information needs to travel between them. Light moves faster than anything else known in established physics. Around Earth, it seems effectively instantaneous. It can circle our planet several times in a second. Yet sunlight does not reach Earth at once. Its journey across the gap takes about 8 minutes and 20 seconds. That delay is happening now. The sun we see is not the sun of this exact moment, but the sun whose light left more than 8 minutes earlier. The number is familiar enough to repeat casually, yet it carries a difficult implication. The empty-looking distance between the handheld sun and the grain-sized Earth is so large that even nature's fastest messenger cannot erase it. And Earth is only the third planet. The distances continue outward, but simply listing larger numbers will not solve the problem. 1 billion kilometers is exact, yet it does not automatically become a place the mind can inhabit. A scale model can preserve the geometry, but it sacrifices visible detail. A compressed picture can preserve the planets, but it sacrifices the gaps. Light time can preserve causal meaning, but it converts space into waiting. To build an honest understanding, we will need all of these views, and we will need to know where each one fails. We must first abandon the idea that a planet has one permanent distance from us. The worlds are not beads fixed along a wire. They are moving bodies on different orbits, continually changing the gaps between them. Only after that motion is restored can the real scale be measured. And once the crowded portrait is gone, a more difficult question appears. If no ordinary picture can hold the planets at their true sizes and separations, how did human beings discover the dimensions of this invisible architecture without first crossing it? The planets are moving. Yet simple distance claims often hide that fact. We say Mars is a certain number of kilometers away, as though it were a town marked beside a fixed road. We say Venus is our nearest neighbor, or Jupiter lies hundreds of millions of kilometers beyond Earth. These statements can be useful, but only after we ask a question that is often omitted. Distance measured from where, and at what moment? Begin with Earth's distance from the Sun. The familiar value of about 150 million kilometers describes the scale of Earth's orbit. More precisely, one astronomical unit is now defined as an exact length. But Earth does not remain exactly one astronomical unit from the Sun at every moment. Its orbit is slightly elliptical, so the actual separation changes during the year. The same is true for every planet. Each follows its own orbit at its own pace. Mercury completes its circuit quickly. Neptune requires more than a human lifetime. None of these worlds waits at a permanent marker while Earth approaches or recedes. This creates several different meanings for one ordinary word. When a reference table gives a planet's distance from the Sun, it usually reports a characteristic orbital scale called the semi-major axis. For a nearly circular orbit, this resembles an average radius. For an ellipse, it is half the longest width of the orbital path. It provides a stable way to compare orbits, even though the planet's actual distance from the Sun is continually changing. But that number does not tell us how far the planet is from Earth. Imagine Earth and Mars moving around the Sun like two runners on separate tracks. Earth runs on the inner track and completes a lap sooner. Mars moves more slowly on the outer track. Sometimes they occupy the same side of the Sun, making the space between them relatively small. At other times they stand on opposite sides, with the Sun and much of both orbits between them. Their separation grows and shrinks because both runners are moving. The track image is useful, but reality is less tidy. Planetary orbits are not perfect circles. They do not all lie in exactly the same plane. Their speeds vary along their paths, and other bodies exert smaller gravitational influences. The analogy explains why the distance changes. It does not calculate the exact distance on a particular date. For that, astronomers use ephemerides, detailed predictions of where celestial bodies will be at specified times. A mission planner asking how far Mars will be during an encounter needs this changing geometry, not merely the average size of Mars's orbit. Even the phrase "closest approach" needs care. Two diagrams may show Earth and Mars aligned on the same side of the Sun and subtract their orbital distances. That gives a clean theoretical picture, but real close approaches vary. The ellipses have particular orientations. The planets rarely arrive at the most favorable point simultaneously. A mathematically possible minimum is not automatically a typical encounter. Venus produces another trap. It can approach Earth more closely than any other planet during favorable geometry, so it is often called Earth's closest planet. But if the question asks which planet remains closest on average over long periods, the answer depends on the definition and calculation being used. Closest can describe a brief encounter, an average separation, or neighboring order from the Sun. One word can hide three different questions. Then there is the distance actually traveled by a spacecraft. A spacecraft does not leave Earth, point toward the location where Mars appears, and follow a fixed, straight line until arrival. Mars would move long before the vehicle reached it. The spacecraft enters its own path around the Sun, designed to intersect Mars's future position. That curved route is longer than the straight separation shown at departure, and its duration depends on much more than the vehicle's headline speed. Launch timing matters. Available energy matters. The desired arrival speed matters. A mission that must enter orbit faces different demands from one that merely flies past. Engineers therefore speak of launch windows, transfer trajectories, and velocity changes, not just the number of kilometers between two dots. This is why different sources can give very different distances for the same planet without contradicting one another. One may list mean distance from the Sun. Another may describe the present distance from Earth. A third may cite a favorable close approach. A mission report may state the length of the route its spacecraft actually followed. Each number can be correct while answering a different question. Light time changes with the same geometry. A radio message to Mars does not always face one fixed delay. When the planets are relatively near, the signal crosses a shorter gap. When they lie far apart, the delay becomes much longer. Mission control must know which geometry applies, because every command and every returned measurement is separated by that finite travel time. The changing delay also reminds us that distance is not merely a line drawn across a map. It controls when one place can affect another. A number in kilometers becomes a weight for information, a limit on control, and a record of motion. So before traveling outward, we need a disciplined vocabulary. Mean heliocentric distance tells us the scale of an orbit around the Sun. Instantaneous separation tells us how far two moving bodies are from one another at a chosen moment. Closest approach describes a particular geometric event and must be dated or qualified. Travel distance describes a designed path, not a road. Light time tells us how long a signal requires to cross the current separation. These distinctions do not make the solar system smaller. They make its scale more honest. The planets are not arranged in a straight row, and their gaps are not frozen. They form a changing system whose geometry never stops. Now we can return to the physical model without pretending that it captures every position forever. We can choose representative orbital scales, reduce every length by the same factor, and ask what remains visible. The answer will reveal something more unsettling than a collection of very large numbers. Shrinking the solar system does not solve the problem of seeing it. It only makes the worlds disappear. Take the sun out of the sky and reduce it to something you can carry. Give it a diameter of 14 centimeters, about the width of a small ball. This will be our linear scale, and unlike the familiar planetary portrait, it will not change when the results become inconvenient. At this size, the real sun has been reduced by a factor of roughly 10 billion. Every planet, moon, and orbital distance must be reduced by the same factor. We are not building a decorative display. We are testing what remains when one rule governs everything. Mercury, the nearest planet to the Sun, becomes a dark speck less than half a millimeter wide. Its representative orbital distance places it almost 6 meters from the ball. Venus is a little over 1 millimeter across and belongs nearly 11 meters away. Earth is also about 1 millimeter wide, but its place is 15 meters from the Sun. Mars is smaller still, less than a millimeter, at a distance of almost 23 meters. The entire inner solar system now stretches beyond a large room, while its 4 planets resemble grains scattered through the air. Nothing about the model looks like the diagram stored in memory. The worlds do not form a colorful chain. Unless each grain is labeled, a person could walk past without seeing it. This is the first cost of honesty. A model that preserves distance loses visible detail. Continue outward. The asteroid belt begins beyond Mars, but it does not become a dense wall of tumbling rocks. On this scale, even a large asteroid would be extremely small, while the region itself would occupy many meters. The objects are separated by immense volumes. Spacecraft can cross the belt because its cinematic image as a crowded obstacle course is false. Jupiter finally gives the eye something larger, though not large enough to repair the model. The greatest planet becomes a sphere about 14 millimeters across, similar to a small marble. Yet it belongs nearly 78 meters from the model Sun. Saturn, excluding the broad visual reach of its rings, is about 12 millimeters wide and weighs around 143 meters away. Uranus would be about 5 millimeters across at roughly 287 meters. Neptune would be a similar tiny bead around 450 meters from the starting point. At Neptune, look back toward the model Sun. It is no longer a dominating ball held nearby. It is a small object almost half a kilometer away. Between it and the outermost major planet lie hundreds of meters in which nearly every visible landmark belongs to Earth, not to the model. The actual solar system contributes scattered specks. Now try to photograph the result. Stand close enough to show Earth's 1 millimeter body, and the outer planets lie beyond the frame. Move far enough back to include Neptune, and Earth may occupy less than a pixel. The issue is not the quality of the camera. It is the ratio between a planet's diameter and its orbital distance. There are ways to make a useful image, but each involves a declared sacrifice. We can enlarge the planets while leaving their orbital positions unchanged. We can compress the gaps while preserving relative order. We can separate size and distance into two diagrams. We can use a logarithmic scale, in which each step represents multiplication rather than equal physical length. These choices reveal patterns that a single linear map conceals. A logarithmic diagram can place Mercury and Neptune on the same page without reducing the inner system to one crowded dot. But equal spaces on that page no longer represent equal distances. It is a map of ratios, not a miniature road. The viewer gains visibility and loses direct spatial proportion. No representation is dishonest merely because it simplifies. The honesty lies in naming what has changed. The physical model also corrects another familiar impression. In photographs, planets seem like enormous presences, filling the frame because cameras approach them or use narrow fields of view. That is appropriate when studying weather, rings, craters, or geology. But the same close view hides how little of the solar system each world occupies. Even Jupiter, with room for more than 1,000 Earths by volume, is a small island within its orbit. The orbit is not a circular track made of material. It is the changing path Jupiter follows through space. Most locations along that vast path contain no planet. Most of the volume above, below, inside, and beyond it contains no major world at all. Calling the system empty, however, can create a different false picture. Interplanetary space contains the solar wind, magnetic fields, energetic particles, dust, radiation, comets, asteroids, and smaller bodies. Gravity extends across every gap. The Sun influences the entire planetary system. Empty, therefore, means sparse in macroscopic objects, not devoid of matter, energy, or physical activity. The model teaches geometry, not everything that exists between the planets. It cannot display an invisible magnetic field. It cannot show thin plasma at the same visual scale as a solid planet. It cannot represent every asteroid without turning selected objects into exaggerated symbols. Every model answers a limited question. Our question is how planetary size compares with planetary separation. For that purpose, the result is decisive. Shrinking the solar system by 10 billion does not make it comfortably visible. It turns familiar worlds into grains and distributes them across nearly half a kilometer. Yet physical distance still has an emotional weakness. Most of the model looks like an ordinary walk. 15 meters can be crossed in seconds. 450 meters is not difficult on Earth. The scale is mathematically faithful, but the experience is distorted because we are walking through the model at a speed with no equivalent in space. To restore meaning, the same geometry needs another measure. Replace footsteps with light. A flash leaves the 14-centimeter sun. It passes Mercury after a little more than 3 minutes on the real scale, reaches Earth after roughly 8 minutes, and continues outward for hours before reaching Neptune's orbit. Now the blank distances acquire duration. The emptiness is no longer unused space on a field. It is a sequence of delays that nothing carrying information can avoid. The next step is to enter the part of the model that still feels closest: Mercury, Venus, Earth, and Mars. They are usually called the inner planets, a compact group of neighboring rocky worlds. But once their motion, light time, and real journeys are restored, even this supposedly local neighborhood begins to separate into islands. The inner solar system is often described as our local neighborhood. 4 rocky planets circle close to the Sun, separated from the giants beyond by the asteroid belt. On a diagram, Mercury, Venus, Earth, and Mars appear to share a compact region. But compact is a relative word. The neighborhood only looks small when compared with what lies farther out. Begin at Mercury. Its orbit has a characteristic scale of about 58 million kilometers from the Sun. Light covers that distance in a little more than 3 minutes. By terrestrial standards, this nearest planetary orbit is already immense. Yet Mercury's closeness to the Sun creates a puzzle. It seems as though it should be the easiest planet to reach. It is not. A spacecraft leaving Earth already moves around the Sun with Earth. To reach Mercury, it must lose a large amount of that orbital energy and fall inward without arriving too fast to conduct its mission. The Sun's gravity accelerates the spacecraft as it descends. Reaching the inner planet can therefore demand a carefully designed series of planetary flybys and course changes. Nearer to the Sun does not mean nearer in the practical language of flight. Venus moves on the next orbit, roughly 108 million kilometers from the Sun. Its size resembles Earth's, and favorable alignments can bring it closer to us than any other planet. That fact encourages a second illusion. If Venus can become our closest planetary neighbor, the gap must sometimes become modest. It does become smaller than most interplanetary separations, but never ordinary. The geometry is temporary. Earth and Venus circle at different speeds, so an approach is followed by recession. A spacecraft must be launched not toward the place where Venus is seen, but toward the point where its orbit and Venus's future position can meet. Even the nearest encounter is a scheduled intersection between moving worlds. Earth occupies the third orbit, with one astronomical unit defining a length of 149,597,870,700 meters. Sunlight takes about 8 minutes and 20 seconds to cross this representative distance. That familiar delay provides the baseline for everything that follows. It also changes the meaning of the present. The sunlight warming a landscape began its journey before the observer saw it. If the Sun could somehow change at this moment, Earth would receive no information about that change until the light had crossed the gap. Distance is therefore not only an amount of space. It separates causes from the moments when their effects can be known elsewhere. Now continue to Mars, whose orbit has a characteristic scale of about 228 million kilometers from the Sun. Comparing that number with Earth's orbital scale gives a difference of roughly 78 million kilometers. But that subtraction is not the normal distance from Earth to Mars. It describes the gap between two representative orbital scales, not the changing line between the planets. At favorable times, Earth catches Mars with both worlds positioned on the same side of the Sun. At unfavorable times, they are separated by a much larger span. The corresponding one-way radio delay changes from minutes to more than 20 minutes. A command sent to a machine on Mars cannot produce an immediate visible response. By the time confirmation returns, the situation that prompted the command may be more than 40 minutes old. This is why a rover is not driven like a remote-controlled car. Mission teams plan activities, send instructions, and wait. The vehicle must protect itself and carry out parts of its work without moment-by-moment steering from Earth. The distance becomes part of the machine's design. Human travel faces the same geometry with far greater demands. Statements such as, "Mars is only several months away," describe particular mission concepts, trajectories, and alignments. They do not provide a permanent travel time. A faster route may require more energy and create a more difficult arrival. A slower path may conserve fuel but increase exposure to isolation and the space environment. The distance cannot be separated from the way the journey is flown. The contrast among these planets reveals why a simple ranking by kilometers is incomplete. Mercury is closest to the Sun, but energetically difficult to approach from Earth. Venus can pass relatively near, but its position changes, and its environment creates other mission challenges. Mars is farther, yet its orbit offers well-studied transfer opportunities. Each destination defeats a different shortcut in our intuition. Still, the raw scale matters. On Earth, landscapes offer continuous evidence of distance. Mountains grow slowly larger. Roads provide milestones. Aircraft cross familiar geography below. Between planets, there is no visible track connecting departure and arrival. After Earth recedes, the destination can remain a point for most of the voyage. Millions of kilometers pass without producing the visual sensation of crossing millions of kilometers. This makes interplanetary distance strangely easy to underestimate. A camera shows the planet at departure, then the planet at arrival. The long middle becomes a shortened sequence or disappears entirely. The viewer remembers two worlds and a transition, not the enormous interval that controlled the mission. The light clock restores that interval. From the Sun, light reaches Mercury's orbital region in a little over 3 minutes, Venus in roughly 6, Earth in a little over 8, and Mars in about 13. These are representative Sun-to-orbit times, not fixed communication delays from Earth. Their purpose is to keep one consistent ruler as the planetary system expands. Even at light speed, the inner solar system cannot be experienced all at once. A flash crossing from one side of the region to another requires time. A radio network spread across these worlds could never behave like people speaking in the same room. Every conversation would be shaped by orbital position and weighting. Yet the inner planets remain a tightly grouped family when viewed against the entire solar system. Mars's orbit lies around 1.5 times Earth's distance from the Sun. Jupiter's begins a different scale of architecture at more than 5 times Earth's orbital distance. The transition is not a boundary wall, but the spaces ahead become dramatically broader. Before reaching Jupiter, a traveler encounters the asteroid belt. Popular images often fill it with closely packed rocks that must be dodged at every moment. The true belt is wide and sparse. Its total population is important for planetary history, but its individual objects are generally separated by enormous gaps. Numerous spacecraft have crossed the region without navigating a continuous maze. This correction matters because the crowded asteroid field repeats the same visual error as the crowded planetary portrait. Objects must be enlarged and brought together so an audience can see them. The resulting image preserves drama while destroying spacing. Beyond that sparse belt, Jupiter appears. Its enormous body may dominate a close photograph, but from the Sun, it occupies an orbit around 5 times farther out than Earth's. Sunlight takes roughly 43 minutes to reach its orbital region. The light that crossed the entire Earth-Sun gap in 8 minutes must continue for more than half an hour beyond Earth before arriving there. That is the threshold where the solar system's scale begins to feel qualitatively different. The inner worlds taught us that neighboring planets are not close in any ordinary sense. The outer worlds will reveal something more extreme. As the planets become larger, the architecture around them expands even faster. The gaps, not the worlds, remain the dominant feature. And this time, The emptiness stretches for light hours. Jupiter does not merely add another planet to the map. It changes the rhythm of the solar system. The four rocky worlds occupy orbits within about 1.5 astronomical units of the Sun. Jupiter's characteristic distance is roughly 5.2 astronomical units, about 778 million kilometers. The leap from Mars to Jupiter is wider than the entire region containing Mercury, Venus, Earth, and much of Mars's orbit. Jupiter itself is enormous. Its diameter is around 11 times Earth's, and its volume could contain more than 1,000 Earths. In a close image, it appears to justify its name as a giant. But place that body honestly within its orbital architecture, and the surrounding gap overwhelms it. A world capable of swallowing Earth many times over still occupies only a tiny location in a path billions of kilometers around. Sunlight requires roughly 43 minutes to reach Jupiter's average orbital region. A signal sent from Earth travels a changing distance, sometimes shorter and sometimes much longer, depending on where both planets are. Even before the outer solar system has properly begun, a conversation across it has become a sequence of departures and delayed arrivals. Jupiter also reveals why traveling outward is not simply a matter of building a faster engine. Its gravity can redirect a spacecraft and change its speed relative to the Sun. A carefully arranged flyby allows the planet's motion to contribute to a new trajectory. The spacecraft does not take energy from nowhere. It exchanges a tiny amount of momentum with the moving planet, whose own change is immeasurably small in practical terms. This technique, called a gravity assist, turns planetary geometry into part of the propulsion system. It can open routes that would otherwise demand far more fuel. But it also reinforces the importance of timing. The planet must be in the right place. The spacecraft must arrive along the right path, and the encounter must produce the required direction afterward. Distance provides the stage. Alignment determines whether the route exists. Beyond Jupiter, Saturn circles at about 9.6 astronomical units from the Sun. Light needs roughly 1 hour and 20 minutes to cover that representative distance. Saturn's rings make the planet appear broad and commanding in photographs, but their visual reach cannot fill the gulf around its orbit. The next giant remains an isolated system of world, moons, rings, and particles surrounded by a far larger domain of open space. At this point, the scale model from earlier has stretched well beyond the dimensions of an ordinary building or garden. With the Sun reduced to 14 centimeters, Jupiter sat almost 78 meters away. Saturn belonged around 143 meters from the starting point. Even these large planets were only marble-sized objects, separated by a walk long enough to erase their visual connection. Then comes another widening. Uranus orbits at about 19.2 astronomical units, nearly twice Saturn's characteristic distance. Sunlight takes around 2 hours and 40 minutes to reach that region. A probe there operates across a divide in which a command and its eventual confirmation can consume a substantial part of a working day. Neptune lies farther still, at approximately 30.05 astronomical units from the Sun. Its average orbital distance is about 4.5 billion kilometers. Light requires about 4 hours and 10 minutes to travel from the Sun to Neptune's orbital region. A round-trip signal between Earth and a spacecraft near Neptune can therefore involve many hours of waiting, with the exact delay changing as the planets move. The word outer can make these worlds sound like points near a boundary. Neptune, however, is not the edge of everything belonging to the Sun. Dwarf planets, trans-Neptunian objects, the Kuiper belt, scattered objects, and far more distant comet reservoirs extend the solar system's story beyond the 8 major planets. But the title's planetary journey reaches its final major world here. Adding more distant populations would change the question before this scale has been understood. Look inward from Neptune. The Sun is still by far the most massive object in the system, yet visually it has become a brilliant, distant point rather than the disk seen from Earth. Sunlight is weaker because the same output spreads over an ever larger area. Earth is not a visible blue landmark waiting near the Sun. It is a tiny moving world hidden within the inner glare and distance. No ordinary family portrait prepares the viewer for this reversal. From Earth, Neptune is a small object in our sky. From Neptune's region, Earth would be an even smaller object near a remote star. The solar system does not offer one privileged image, in which every world remains clearly visible. Each viewpoint loses almost everything else. One mission demonstrated both the severity of the distances and the power of rare geometry. Voyager 2 visited Jupiter, Saturn, Uranus, and Neptune. Its path was not a routine outward tour that could begin at any time. The outer planets occupied a favorable arrangement that allowed successive gravity assists. Each encounter helped shape the route toward the next. This did not make the planets close. It made their motion useful. Voyager 2 still required years to cross the gaps, and Neptune was reached only after a journey spanning much of a decade. The achievement depended on accepting the solar system as a moving gravitational system rather than treating the planets as stationary stops along a straight highway. The mission also exposes the difference between a voyage and the edited memory of a voyage. Its famous images preserve brief encounters: Jupiter's clouds, Saturn's rings, Uranus's muted atmosphere, Neptune's blue disk. Those images are dense with detail. The years between them contain no equivalent sequence of approaching landmarks. Most of the route is represented by trajectories, radio signals, engineering checks, and time. That long middle is where the true solar system exists. It is tempting to describe the expanding distances as a simple pattern, with each planet placed farther out than the last by a regular amount. The actual architecture is not a uniform staircase. Differences between orbital scales vary. Planetary formation, migration, resonances, and gravitational history shaped the arrangement. For this documentary, the essential point is narrower. The outer planets occupy a region enormously broader than the compact drawings imply. The light clock makes the progression difficult to ignore. A signal leaves the Sun. Mercury receives it after minutes. Earth receives it after a little more than 8 minutes. Jupiter waits roughly 43 minutes. Saturn waits more than an hour. Uranus waits several hours. Neptune receives sunlight more than 4 hours after it began the journey. At each orbit, the same light has traveled without slowing. The growing delay belongs entirely to the expanding space. The widening changes probability. A spacecraft crossing the outer system is not likely to stumble upon a world by accident. Reaching one demands prediction across years. The target may be enormous compared with Earth, yet from the scale of its orbit, it remains a moving point that must be met. And yet astronomers knew the relative arrangement of these worlds long before any spacecraft crossed the asteroid belt, long before radio echoes returned from another planet, and long before a kilometer had been formally attached to the astronomical unit. That achievement creates a different kind of distance puzzle. From Earth, the planets first appeared as wandering points of light. No observer could look down from above and measure their orbits with a ruler. No camera could capture an honest family portrait. Still, patterns in their motion revealed an underlying architecture. The next stage of the story therefore moves backward in time. The question is no longer how long light or spacecraft need to cross the solar system. It is how human beings discovered the proportions of a system they could not see from the outside. The answer begins with a map that had the correct relationships, but no known scale. Astronomers would learn that the 8 planetary distances were not 8 independent mysteries. Solve one missing length, and the dimensions of the entire system could emerge. For most of human history, the planets were not known as distant worlds, arranged across a vast system. They were lights that refused to behave like the fixed stars. Night after night, the stellar background preserved recognizable patterns. The planets moved among those patterns. Sometimes they advanced in one direction, slowed, appeared to reverse, and then resumed their earlier motion. Their wandering could be recorded with great care, but the view from Earth mixed their movement with our own. The difficulty was not simply that the planets were far away. The observer was standing on one of the moving bodies while trying to reconstruct the motion of all the others. For centuries, astronomers developed geometrical systems that could predict where the planets would appear in the sky. These systems were not foolish. They responded to real observations and, with enough refinement, could achieve useful predictions. But prediction alone did not guarantee that the underlying physical arrangement had been understood. The major change came when the Sun replaced Earth at the center of the planetary architecture. In a Sun-centered system, the strange loops of retrograde motion could be understood as effects of relative motion. Earth could overtake an outer planet, changing the direction in which that planet appeared against the distant stars. The wandering light did not need to reverse its orbit. The observer's moving viewpoint helped create the appearance. Even this new arrangement left a demanding problem. What paths did the planets follow, and what rule connected their distances with their motion? Johannes Kepler approached that problem with an extraordinary observational inheritance. Tycho Brahe had spent years measuring planetary positions with precision unmatched before the telescope. The data did not present a theory by themselves. They placed restrictions on any theory that hoped to survive. Mars became especially important. Its apparent motion resisted the demand that planetary paths be perfect circles. Small discrepancies might have been dismissed as observational error, but Kepler treated them as evidence that the model was wrong. The orbit had to change. The replacement was an ellipse, a closed curve that resembles a stretched circle. The Sun occupies one focus of the ellipse rather than its exact geometric center. A planet, therefore, does not remain at one fixed distance from the Sun. It moves closer and farther as it travels around its path. This solved more than a problem of shape. Kepler also found that a planet changes speed along its orbit. It moves faster when nearer the Sun and slower when farther away. The solar system was not a set of lights attached to uniformly turning circles. It was a dynamical arrangement whose geometry and timing belonged together. Then came the relationship that matters most for the scale of the system. Kepler discovered that the time a planet takes to complete an orbit is connected to the size of that orbit in a precise way. Planets with larger orbits require longer periods, and the relationship follows a common mathematical pattern. The full equation is less important here than its power. If Earth's orbital period and representative orbital size are treated as the reference, the period of another planet reveals the size of its orbit relative to Earth's. The years of Jupiter and Saturn were no longer merely calendar curiosities. They became clues to distance. This gave astronomy something remarkable: a ruler made from time. Suppose Earth's orbital scale is labeled 1 unit. Kepler's relationship places Mars at roughly 1.5 of those units, Jupiter at about 5.2, and Saturn near 9.6. Later discoveries could join the same framework. Uranus and Neptune would occupy much larger values, but they would still belong to the same proportional architecture. The map now had structure. Astronomers could compare one orbit with another. They could say that Jupiter lay several times farther from the Sun than Earth, or that Neptune's orbital scale was roughly 30 times Earth's. The ratios were not guesses based on how bright the planets appeared. They emerged from repeated observations of motion. This was a profound gain in knowledge, even before the missing unit was solved. A model could now be tested as a connected whole. If a measured period implied one orbital proportion, later observations had to agree with it. The heavens were becoming more than a collection of separate tracks. They were becoming a system governed by relationships, where timing at one world helped locate another. Precision in watching motion could reach across space without any observer physically leaving Earth. Yet the map had no ordinary ruler. Calling Earth's orbital scale 1 astronomical unit did not reveal how many kilometers that unit contained. It was like possessing a perfectly proportioned plan of an unknown building. Every room has the correct size relative to every other room. The corridors connect properly, but the plan contains no scale bar. One room might be 1 meter wide or 100 meters wide, and every ratio on the page would remain unchanged. This limitation divided the problem into 2 different achievements. Relative scale came from orbital relationships. Absolute scale required attaching one known physical length to that entire pattern. The distinction is easy to miss because modern tables print astronomical units and kilometers side by side. The numbers appear equally available. Historically, they came from different kinds of reasoning. Kepler could organize the solar system without knowing the modern value of the Earth-Sun distance. His rule gave the architecture before astronomy possessed its precise dimensions. That reversal changes the original mystery. It was not necessary to measure the distance to Mercury, then Venus, then Mars, then Jupiter, one independent road at a time. If their orbital ratios were trustworthy, one successful absolute measurement could calibrate the whole system. Find the length of one astronomical unit, and the relative distances would inherit real units. The challenge was severe, because direct methods available on Earth seemed too small for the task. No chain could stretch toward the Sun. No traveler could carry a surveyor's instrument to another planet. Brightness was unreliable because worlds differ in size, reflectivity, phase, and atmosphere. Apparent diameter alone could not provide a secure answer without other knowledge. Astronomers needed geometry. On Earth, surveyors could determine the distance to an inaccessible point by observing it from 2 known locations. The target appears against a slightly different background from each position. Measure that angular shift, know the baseline between the observers, and a triangle can reveal the missing distance. The effect is called parallax. It can be experienced by holding a finger in front of the face and alternating between the left and right eye. The finger appears to move against the background because each eye views it along a different line. A nearby object shifts more than a distant one. For planetary measurement, however, the shift is tiny. The baseline between two observing sites is large on human scales, but small compared with interplanetary space. Accurate positions, synchronized observations, reliable clocks, careful knowledge of geography, and favorable celestial geometry all matter. A small error in angle can become a large error in distance. Still, the principle offered exactly what the scale problem required. Earth itself could become the baseline. Observers separated across its surface could look toward the same planet and construct a triangle extending into space. This did not yet provide the complete modern answer. It supplied a path from local measurement to cosmic distance. A known separation on Earth could help determine a planetary distance. That distance could calibrate the astronomical unit. Kepler's relative map could then convert one result into the scale of the other orbits. The 8 planetary distances had collapsed into one experimental target. That is the central transformation. The solar system remained too large to see from outside, and too sparse to fit into an honest portrait. But its motions formed a connected rulebook. Each orbit was no longer an isolated mystery. The planets revealed one another through a shared pattern. Now the missing scale had to be extracted from observations made on a single moving world. The first great attempts would use Mars, distant observing stations, and the width of Earth as part of an enormous triangle. Later, the passage of Venus across the Sun would send observers around the globe in pursuit of the same elusive length. The problem was no longer where every planet was. The problem was how accurately humanity could measure one angle. In 1672, Mars offered astronomers a rare opportunity. The planet was approaching a favorable position, and observers separated by thousands of kilometers could use Earth itself as the base of an immense triangle. Giovanni Domenico Cassini observed from Paris. Jean Richet traveled to Cayenne, near the northern coast of South America. The distance between their stations was known well enough to serve as a baseline. If both men recorded Mars against the background stars at corresponding times, the planet would appear in a slightly different position from each location. That apparent shift was extremely small. Nothing about Mars visibly announced that two lines of sight were meeting there. The result had to be extracted from precise positional measurements, careful timing, and knowledge of the observer's locations. The geometry followed the same principle as viewing a nearby finger with alternating eyes. But the human face had been replaced by a large span of Earth, the finger by another world, and the distant room by the stars. Once the angle at Mars was estimated, the known baseline allowed astronomers to infer a distance. Then the established relative orbital relationships could connect that result to the Earth-Sun scale. One terrestrial measurement could reach Mars, and Mars could help calibrate the entire planetary system. The outcome was not the modern value with modern precision. Historical reconstructions differ in how they describe the exact result and uncertainty. Observations from the 17th century faced limitations in instruments, clocks, atmospheric conditions, and geographic knowledge. But the campaign produced one of the first credible estimates of the absolute scale of the solar system. The dimensions were no longer only proportions. This is the midpoint of the mystery. The distances to the planets had seemed like separate voids, each demanding its own impossible measurement. Kepler's rule had already connected their proportions. Parallax now showed that a single absolute calibration could give physical meaning to the whole map. The central problem had changed. Astronomers did not need to stretch a ruler from Earth to every orbit. They needed to improve one measurement until the unit beneath all the others became trustworthy. The important revelation was not a comparison between the estimated unit and a journey. It was the transfer of certainty from the measurable to the unreachable. Astronomers knew the separation between observing sites. They measured a difference in direction or duration. From that evidence, they reconstructed a triangle whose far side extended across interplanetary space. The method did not make the void visible, and it did not make the worlds feel close. It made the scale accountable. Another observer could examine the assumptions, repeat the geometry later, compare the result, and identify the sources of disagreement. The solar system was becoming not only imaginable through models, but testable through shared measurement. Mars was helpful, but the angular shift remained tiny. A more favorable celestial event promised another route. Venus sometimes passes directly between Earth and the Sun, appearing as a small dark disk crossing the bright solar face. Such transits are rare, but they can be observed from widely separated locations on Earth. Edmund Halley recognized how valuable this geometry could be. Observers at different latitudes would see Venus trace slightly different paths across the Sun. Those path differences would affect the times when Venus appeared to enter and leave the solar disk. If the observers knew their positions and measured the transit times accurately, geometry could yield the solar parallax and therefore the astronomical unit. The proposal transformed a distant planetary crossing into a global measurement experiment. The essential quantity was not the size of the Sun in the sky or the brightness of Venus. It was the small difference between observations made from separated points on Earth. The transits of 1761 and 1769 inspired expeditions to distant observing sites. Astronomers and supporting crews traveled across oceans and continents because a longer terrestrial baseline improved the geometry. The same event had to be observed under different skies, with clocks, instruments, coordinates, and methods capable of being compared afterward. The scale of the effort reflected the scale of the question. No single observer owned a baseline large enough. The planet itself crossed the Sun only once for everyone, but Earth supplied many viewpoints. Knowledge emerged by combining them. The experiment looked simple in principle. Record the instant when the edge of Venus first touches the Sun. Record when the planet moves fully onto the solar disk. Repeat the process as it exits. Compare durations from different locations, then solve the geometry. Reality was less cooperative. Near the moments of contact, the silhouette of Venus could appear stretched toward the dark edge of the Sun, creating what became known as the black drop effect. Atmospheric turbulence, optical limitations, focus, and the Sun's own changing brightness near its edge complicated the exact timing. Weather could erase an entire observation after years of preparation. Clocks and geographic positions introduced additional uncertainty. Different observers could watch the same transit and disagree about the precise instant of contact. Because the desired effect was small, seconds mattered. An uncertainty that seemed minor at the telescope expanded when translated into the dimensions of the solar system. The campaigns, therefore, did not produce one flawless number delivered by a single decisive observation. Their power came from accumulating and comparing many imperfect measurements. Analysis refined the estimate, revealed disagreements, and showed where the method reached its limits. This is how major measurements often advance. A beautiful geometrical idea meets instruments, weather, human judgment, and an imperfect natural event. The result is not the abandonment of the idea. It is a clearer understanding of how much confidence the evidence can support. The Venus transits improved knowledge of the astronomical unit and made the search for solar system scale an international scientific project. Later transits and other methods continued the refinement. But the underlying achievement was already profound. An interval too large to cross could be determined by watching a small shadow move across sunlight. Consider what the calculation accomplished. An observer did not see the astronomical unit directly. The telescope supplied an angle or timing. Geography supplied the baseline. Orbital theory supplied the relationships among Earth, Venus, and the Sun. Mathematics combined those ingredients into a distance. The answer, therefore, depended on a network of knowledge. An error in the orbit affected the geometry. An error in station location affected the baseline. An error in contact timing affected the inferred angle. Precision required the pieces to agree. This does not weaken the measurement. It explains why scientific distance is different from visual distance. On Earth, a person may judge that a nearby object looks several meters away. Across the solar system, appearance alone is insufficient. Distance becomes an inference constrained by multiple observations. The same logic would later reach far beyond the planets. Parallax would help determine distances to nearby stars using Earth's changing position around the Sun as a baseline. The unit that astronomy struggled to calibrate would itself become part of a larger cosmic ruler. But that wider distance ladder belongs to another story. Here, the task remains the planetary system. By the beginning of the modern era, astronomers possessed increasingly refined estimates. Yet optical methods still demanded the measurement of tiny angles, or delicate contact times. The precision of the final scale remained tied to the difficulty of seeing extremely small differences through an atmosphere. A new method would change the kind of observation being made. Instead of waiting for a planet to align with the Sun, researchers could send a signal toward a planet. Instead of inferring distance from a tiny apparent shift, they could measure how long the signal took to travel out and return. Geometry would remain necessary because both worlds were moving, but elapsed time would become the central observable. The concept sounds straightforward only because the required technology is now familiar. A radar pulse leaves Earth at the speed of light. It spreads as it travels, reaches a planet, and only a tiny fraction of its energy returns. By the time the echo arrives, it is extraordinarily weak. The receiving system must distinguish that predicted whisper from noise. Success would require powerful transmitters, sensitive antennas, accurate clocks, and orbital predictions good enough to identify when and where the echo should appear. The old proportional map was not discarded. It helped guide the experiment designed to improve its scale. The hunt for one absolute length was approaching a decisive reversal. For centuries, finite light speed had expressed the intimidating size of the solar system. Now that same delay could become a ruler. The next measurement would not ask how far a planet seemed to shift. It would ask when the echo came home. In 1961, a radio signal left Earth and traveled toward Venus. It carried no picture and required no observer on the planet. Its purpose was to cross the gap, strike the distant world, and return as evidence of the time spent in between. The experiment took place during the early age of planetary radar. At Goldstone in California, researchers directed transmitted energy toward Venus, the bright planet whose surface remained hidden beneath clouds. The target was enormous, but the task was not easy. A radio beam spreads as it travels. Only part of it reaches the planet. Only part of that energy is reflected in Earth's direction, and only a minute fraction returns to the receiving antenna. The echo was not expected to sound like a clear reply. It would be a weak signal buried among noise, altered by relative motion, and distributed across a predicted range of frequencies and arrival times. Detecting it required knowing where to look before it appeared. That prediction depended on the very planetary map the experiment was designed to improve. Researchers used existing orbital models to aim the transmission and estimate the echo's return. If the assumed scale was slightly wrong, the predicted delay would also be wrong. The search, therefore, had to cover uncertainty, rather than wait for one perfectly known instant. When definite echoes from Venus were identified, elapsed time became a planetary ruler. The central principle can be stated simply. A radar pulse travels at the speed of light. Measure the time between transmission and reception. Multiply that duration by light speed, then divide by 2, because the signal crosses the distance outward and back. The result gives the range between the observing system and the reflecting region of the planet. But the simple equation is only the center of a larger measurement. Earth rotates while the experiment occurs. Earth and Venus move along their orbits. The reflecting surface is not a single ideal point, and Venus itself rotates. The signal changes frequency because of relative motion. Instrument delays, atmospheric effects, and uncertainty in the predicted orbit must be understood. The measurement was therefore not a handheld rangefinder aimed at a stationary wall. It was an echo exchanged between moving worlds, interpreted through a dynamical model. That combination is essential. Observation and theory were not rivals. The model predicted where the echo should be. The echo tested and corrected the model. Improved orbital information then supported better predictions for later observations. Each cycle reduced uncertainty. The 1961 Venus radar work at Goldstone greatly refined the astronomical unit. A historical account from the Jet Propulsion Laboratory describes an early estimate accurate to roughly 500 kilometers. Across a distance near 150 million kilometers, that represented an extraordinary improvement and helped prepare the navigation framework for planetary missions. Other groups also pursued planetary radar during this period, and later measurements extended and improved the method. The achievement was not that one antenna single-handedly completed the solar system forever. It was that radar introduced a powerful new kind of direct-range evidence into the network of astronomy. For centuries, the scale had been inferred from angular differences, Mars shifting against stars, Venus tracing different paths across the Sun. Radar did not eliminate geometry or orbital theory, but it replaced the need to resolve a tiny visual angle with the ability to measure a travel time. The light clock had become an instrument. Imagine the returning energy as evidence with no drama. Nothing crosses the sky. Venus does not flash when the signal arrives. The meaningful event occurs inside instruments, timing records, and comparisons between expectation and detection. Yet the quietness makes the result more powerful. A measurable delay has survived a journey to another planet and back. The experiment converts an interval that no observer can watch into a number that can be checked. It shows why precision is cumulative. One echo improves the predicted orbit. An improved orbit sharpens the search for an echo. Repeated measurements expose errors that a result might conceal. Confidence grows through agreement across time, instruments, teams, and methods, not through spectacle. This is the strongest reversal in the story. Earlier, light time exposed how far the planets were. 8 minutes to Earth, tens of minutes to Jupiter, hours to Neptune. Every delay made the emptiness larger. In radar astronomy, delay carried the answer back. The obstacle became the measurement. The echo also connected abstract scale with practical navigation. A spacecraft sent toward another planet must arrive where that planet will be, not where an uncertain ephemeris places it. Small errors at launch can grow across millions of kilometers. Better estimates of the astronomical unit and planetary orbits help determine trajectories, schedule course corrections, and interpret tracking data. As spacecraft began traveling through the solar system, they became additional measurement points. Radio systems could determine range through signal travel time and infer motion through frequency shifts. Tracking over many observations allowed navigators to refine spacecraft paths, planetary positions, and the dynamical models connecting them. No single observation carries the entire burden. Modern planetary ephemerides combine many kinds of data across long periods. Radar ranging, spacecraft tracking, optical observations, and other measurements are fitted within models that account for gravitational interactions and necessary relativistic effects. The result is not a frozen chart. It is a continuously tested prediction of motion. That distinction explains how mission teams can aim for a small region near a planet years before arrival. They do not possess a photograph of the future solar system. They possess a model whose predictions have survived repeated comparison with signals and observations. Precision has become operational. The map is accurate enough to act upon. Yet a final change in the meaning of the astronomical unit must be made clear. Historically, the unit was tied to the measured scale of the Earth-Sun system and refined as observations improved. In 2012, the International Astronomical Union defined one astronomical unit to be exactly 109,597,870,700 meters. The word exactly matters. The astronomical unit is now a fixed, defined length, not a claim that Earth always remains that exact distance from the Sun. Earth's orbit is elliptical, so its instantaneous separation continues to change. Nor does the definition stop astronomy from making measurements. Instead, it provides a stable conversion. While quantities such as positions and gravitational parameters are determined through observation and modeling. This is similar to defining a standard unit without claiming that every object measured in that unit becomes fixed. The ruler is fixed. The system being measured continues to move. Modern ephemerides reflect this updated framework. Coordinates can be expressed in astronomical units, but the unit itself no longer needs to be repeatedly re-estimated as a variable length. Observations refine the physical model rather than alter the definition of the ruler. The journey from Kepler to radar therefore contains several distinct levels of knowledge. Kepler supplied ratios among orbital scales. Parallax and transit observations attached an approximate absolute length. Radar replaced delicate angular inference with precise signal timing. Spacecraft tracking expanded the evidence across the system. A formal definition stabilized the unit used to express the result. At no stage did science simply look at a complete solar system and read numbers from it. The architecture emerged from relationships among motion, geometry, time, and repeated tests. That is why the distances deserve confidence, even though they resist direct human experience. They are not supported by one analogy or one dramatic measurement. Independent methods connect to the same dynamical system. A mistake large enough to make the solar system substantially smaller would not remain hidden in a table. It would cause radar echoes to arrive at unexpected times, spacecraft to miss their targets, and planetary positions to drift away from prediction. The successful arrival of interplanetary missions is therefore more than engineering spectacle. It is continuing evidence that the map works. A spacecraft can cross a gap that no image represents honestly, because navigation does not depend on compressing that gap into a picture. It depends on predicting motion and measuring signals. This achievement resolves the historical question, but creates another. If the solar system can be mapped with such precision, why are journeys across it still described with such uncertainty? Why can two missions to the same planet take different amounts of time? Why can a planet that is geometrically nearer demand more energy than one farther away? The answer begins by abandoning the final piece of roadmap intuition. Knowing the distance between two moving worlds does not define the path between them. A spacecraft leaves Earth already traveling around the Sun. It must reshape that motion into a new orbit, meet a target that will not wait, and often surrender speed when it arrives. The measured gap is real, but it is only one part of the journey. Radar gave the solar system a precise ruler. Orbital flight would reveal why no ruler, however accurate, can tell us by itself how difficult a planet is to reach. Once the distance between two places is known, travel time seems like a simple calculation. Divide distance by speed. The method works reasonably well for a car following a road or an aircraft crossing a mapped route. Applied to planets, it produces an answer that may be numerically tidy and physically meaningless. The problem begins before a spacecraft leaves the ground. Earth is not a stationary platform. It carries everything on its surface around the Sun at tremendous speed. A launched spacecraft inherits that motion. Even after escaping Earth's immediate gravitational control, the vehicle does not enter a motionless void. It occupies its own orbit around the Sun. Traveling to another planet means changing that orbit. Imagine Earth and Mars at a favorable alignment. A straight line can be drawn between them, but a spacecraft cannot simply follow that line while both planets wait. Mars continues along its orbit. Earth moves behind the departing vehicle. The Sun's gravity curves the spacecraft's path. Mission designers must aim toward an intersection in space and time. The target is not Mars's present location. It is Mars's future location when the spacecraft arrives. One efficient approach is represented by a Hohmann transfer. The spacecraft departs one approximately circular orbit and enters an ellipse that touches the orbit of the destination. The transfer uses carefully timed changes in velocity rather than continuous thrust across the whole journey. For travel outward, the spacecraft increases its heliocentric energy, so the far end of its new orbit reaches the target's orbital region. This route is efficient under its simplifying assumptions, but efficiency has a cost. time. The spacecraft coasts along a large part of the transfer ellipse. A faster route may be possible, but it generally demands greater changes in velocity, more propellant, or another propulsion strategy. There is no single travel time hidden inside the distance. The change in velocity required by a mission is commonly described through delta V. The term does not mean the spacecraft's highest speed. It measures the cumulative velocity changes needed to reshape the trajectory, escape or enter gravitational regions, correct errors, and achieve the required final state. This creates a map very different from a map of kilometers. Two destinations separated by similar geometric distances can demand different delta V. A world that passes close to Earth may still be difficult to enter orbit around. A distant target may become reachable through gravity assists that reduce the propellant carried from launch. Mercury is the clearest correction to the belief that closer means easier. It lies inward, nearer the Sun. A spacecraft traveling there must shed much of the heliocentric energy it shared with Earth. As it falls toward the Sun, gravity accelerates it. Arriving beside Mercury is not enough. A mission that needs to orbit must avoid rushing past at excessive relative speed. Repeated flybys of planets can gradually reshape the orbit. Each encounter changes the spacecraft's velocity relative to the Sun, allowing a mission to approach Mercury under manageable conditions. The path can take years and appear indirect on a simple map. That apparent detour is not a failure to choose the shortest line. It is a response to the energy structure of the solar system. Mars presents a different design. Launch opportunities repeat when Earth and Mars return to favorable relative positions. A mission that misses the window cannot recover by aiming at where Mars used to be. It must spend additional energy, accept another trajectory, or wait for the geometry to improve. Arrival also changes the problem. A flyby needs only to pass through a scientifically useful region. An orbiter must reduce its speed relative to the planet enough to be captured. A lander must survive descent. A sample return mission must later climb away and place material on a route back to Earth. The same destination supports many different journey requirements. Jupiter and the outer planets reveal the usefulness of gravity assists. During a flyby, the spacecraft enters the planet's moving gravitational environment and leaves along a changed direction. In the Sun-centered frame, it can gain or lose energy through a minute exchange of momentum with the planet. The giant world's orbit supplies a moving gravitational opportunity. This does not violate conservation of energy. The planet changes too, but its mass is so enormous that the effect on its orbit is imperceptibly small for mission purposes. The spacecraft receives a change that can determine whether the next destination is reachable. Voyager 2's route through the outer planets depended on this logic. Jupiter helped shape the path toward Saturn, and later encounters continued the sequence toward Uranus and Neptune. The worlds were still separated by years of flight. Their motion created a chain of usable encounters. Now the phrase "distance to a planet" has acquired another layer. There is the straight-line separation at a chosen moment. There is the orbital scale around the Sun. There is the length of the flown curve. And there is the energetic distance expressed by the velocity changes required to complete a particular mission. None of these quantities cancels the others. Kilometers still matter. A longer route requires time, navigation, power, communication, and survival. But kilometers alone cannot reveal whether the spacecraft arrives too fast. whether the launch vehicle can provide the departure energy, or whether the target is positioned to meet the transfer. The road analogy fails because roads constrain the route, while engines overcome resistance along it. Interplanetary space offers no road, and a coasting spacecraft does not need to burn fuel merely to keep moving. Propulsion is used primarily to alter motion. Gravity then curves the path continuously. This way of thinking explains why mission paths often look wrong in an illustration. A transfer curve may seem to miss its target because the image freezes the destination. When time is allowed to advance, the planet moves into the meeting point. The drawing must represent both geometry and sequence. Without that motion, an efficient trajectory resembles an arc. With it, the arc becomes the reason contact is possible. The spacecraft is not wandering through excess distance. It is following an orbit whose timing matches another orbit. Every encounter is therefore a prediction made physical. Engines begin the change, gravity carries most of the journey, and navigation corrects the difference between the planned intersection and reality. Reaching a planet means successfully arriving at the place, at the correct time, with a velocity the mission can use. This is why simply attaching the speed of a spacecraft to every destination produces misleading travel estimates. A quoted speed may describe a brief maximum relative to the Sun, a planet, or Earth. It may occur at a point where gravity has accelerated the craft. That number cannot be multiplied forward, as though the vehicle will maintain the same useful direction and speed to any chosen world. Reference frames matter. A spacecraft can be fast relative to one body and slow relative to another. Arrival depends on relative velocity between the craft and target. A probe racing through a planet's neighborhood may be ideal for a flyby and useless for entering orbit without an additional braking method. Mission designers, therefore, do not ask only, "How far is the planet?" They ask when it can be reached, what launch energy is available, what trajectory meets it, how fast the spacecraft arrives, what corrections are possible, and what final orbit or encounter the mission requires. The answer can include trade-offs rather than one optimum. A faster journey may reduce exposure to some hazards, but require more mass in propulsion. A slower path may permit gravity assists or lower energy, while extending operations and communication demands. Scientific goals, spacecraft lifetime, power, cost, and risk influence the route. This deeper model does not make distance less intimidating. It removes the comforting idea that a sufficiently fast vehicle turns every planet into a straightforward destination. The solar system is not merely large, it is in motion, and successful travel requires joining that motion with precision. The difference can be expressed as a change in the governing question. On a road, we ask how quickly a vehicle can cross the space between departure and destination. In orbital flight, we ask what change of motion will cause two independently moving paths to intersect under acceptable conditions. That is why the precisely measured map from radar is necessary but insufficient. It tells navigators where the worlds are and supports predictions of where they will be. Orbital mechanics determines the family of paths that can connect those positions. Propulsion and mission design select among them. Once a spacecraft arrives, however, the distance does not disappear. The vehicle may be orbiting the target, functioning exactly as planned, while Earth remains separated by millions or billions of kilometers. Every command must still cross that gap. Every image and measurement must travel back. The delay cannot be solved by a better trajectory after arrival. It cannot be overcome by using more fuel. It is set by the finite speed at which information propagates. So the next layer of the solar system is not a map of places or transfer paths. It is a network of delayed causes and delayed knowledge. The farther a mission travels, the less it can depend on Earth for immediate judgment. Distance becomes autonomy, prediction, and waiting. A spacecraft can arrive exactly where navigation predicted and still remain beyond immediate reach. Its instruments may be operating. Its antenna may be pointed toward Earth. Its target may fill the camera. But every exchange with the people who built it must cross the distance at light speed. Consider a single command sent to Mars. Mission Control prepares the instruction, checks it, and transmits it through a large antenna. The radio signal leaves Earth and moves across the changing separation between the planets. Depending on their positions, the journey takes several minutes or more than 20. During that interval, nothing on Earth can alter the command. It is already traveling. Mars continues moving. The spacecraft continues operating. If conditions change after transmission, the new information cannot catch the earlier signal by moving faster. When the instruction arrives, the spacecraft receives and interprets it. Perhaps the command begins an observation, moves a mechanism, or directs a rover along a planned route. Information describing the result must then be transmitted back. That return signal faces another interplanetary crossing. By the time Mission Control knows what happened, the complete exchange may represent tens of minutes. The people on Earth are not watching an action unfold live. They are receiving a record of an event that has already occurred, in response to a decision made earlier still. This is distance expressed as causality. The delay grows across the solar system. Near Jupiter, one-way communication with Earth varies with orbital geometry, but can require tens of minutes. At Saturn, Uranus, and Neptune, the wait becomes measured in hours. A request, response, and human decision can occupy a large part of a day. No stronger transmitter can remove this minimum delay. Greater power can help a weak signal remain detectable. Larger antennas can recover faint data. Better encoding can protect information against errors. None of these changes allows the message to outrun light. Deep space missions must therefore be designed for separation from their operators. A spacecraft needs onboard systems that monitor its condition, respond to certain hazards, preserve power, protect instruments, and enter safe configurations when something unexpected occurs. Mission teams can plan these behaviors, but they cannot personally intervene at the instant of every problem. Autonomy does not mean that a distant spacecraft makes every scientific decision alone. Many activities are prepared on Earth and sent as command sequences. The vehicle executes those sequences later, while onboard software handles defined conditions that cannot wait for a reply. Responsibility is distributed across prediction on Earth and immediate response aboard the machine. Navigation follows the same delayed structure. Tracking stations receive radio signals that left the spacecraft in the past. From timing, frequency changes, and other measurements, teams estimate where the vehicle has been and how it is moving. They use a dynamical model to predict its future path, calculate a correction, and transmit instructions that will arrive later. Every step crosses time as well as space. The estimate concerns an earlier state. The correction is designed for a future state. The spacecraft performs it before Earth can see the result. Successful navigation depends on connecting these separated moments accurately. The radar experiment at Venus contained this same pattern in compressed form. A signal departed, reflected from a moving world, and returned after a measurable delay. What served there as a ruler becomes, in mission operations, the unavoidable tempo of exploration. This unifies the story's apparently separate problems. The familiar planetary portrait failed because it removed the gaps. The scale model restored those gaps but made the planets disappear. The light clock converted space into delay. Parallax and radar used geometry and delay to measure the system. Orbital mechanics used the measured map to predict intersections. Communication reveals that the gaps continue governing a mission even after the intersection succeeds. Distance is not only where a planet is. It determines when knowledge can arrive and when a decision can have an effect. For robotic exploration, engineers can adapt. A rover can stop when it detects danger. A probe can store data until a communication opportunity. A spacecraft can carry sequences covering hours or days. The design assumes that Earth will often learn about a critical event only after the event is over. For human travel, the same limit becomes more personal. A crew near Mars could communicate with Earth, but not through natural real-time conversation. Each question would be followed by a wait. Advice from doctors, engineers, or family would arrive after the circumstances had changed. The crew would need authority, knowledge, and resources to act locally. This does not mean distant crews would be abandoned. Communication, planning, and support would remain essential. It means support could not imitate a nearby control room. Distance would change the relationship between Earth and the travelers. The delay also changes observation itself. When a spacecraft sends an image, the scene in that image is already in its past by the time Earth receives it. The farther the craft, the older the information on arrival. This is not a flaw in the camera or network. All observation across distance depends on signals that require time. Even within the solar system, there is no operational view of every planet at one shared instant arriving on Earth. Images and measurements collected from different distances began their journeys at different times. Scientists can use models to compare states within a chosen time framework. But nature does not deliver a simultaneous family portrait. The word now becomes local. Earth has its present events. A spacecraft near Neptune has its own immediate surroundings. Earth can learn about those surroundings only after the signal crosses billions of kilometers. By then, Neptune's region has continued evolving. This idea should not be exaggerated into mystery. Mission teams routinely account for light time. Astronomers distinguish when a signal was emitted from when it was received. Relativity provides the deeper framework for time and simultaneity. But the practical point here requires no advanced mathematics. Information cannot arrive before it has crossed the space between source and receiver. That simple rule gives the solar system a hidden structure. The planets are connected, but never instantaneously. Every link has a delay that expands and contracts as the worlds move. A network spread across the planets would have no universal conversational rhythm. Its members would live inside overlapping schedules of departure, transit, and arrival. Imagine sending one question outward. Mars receives it after minutes. A probe near Jupiter receives it later. A mission near Saturn, Uranus, or Neptune waits longer still. Their replies return on different timelines. The solar system answers as a sequence, not a chorus. This is why the gaps are more than visually blank regions. They are physical intervals with consequences. They require spacecraft autonomy, predictive navigation, stored commands, patient science, and trust in machines operating beyond immediate supervision. The network perspective changes what success looks like. A mission is not successful because distance has been defeated. It succeeds because every stage was designed around distance. Engineers predict when communication is possible, choose what information deserves limited transmission capacity, and prepare the spacecraft for periods when Earth cannot help. Scientists wait for data that may describe an observation completed hours earlier. The delay becomes ordinary inside operations, even while remaining extraordinary in human terms. This is a form of adaptation. Civilization extends its senses across the solar system, but those senses do not return an instantaneous experience. They return timed evidence, assembled patiently into knowledge. They also explain why the solar system can be precisely known without ever becoming emotionally compact. We can calculate the location of a spacecraft, predict an encounter, and schedule a signal. Yet every successful calculation confirms the scale by respecting the delay. Precision does not remove the distance. It demonstrates it. The evidence has now converged. Planet sizes and orbital gaps explain the failure of ordinary pictures. Kepler's rules explain the relative architecture. Parallax and radar explain the absolute scale. Orbital mechanics explains the journey. Communication delay explains the continuing separation after arrival. But one phrase remains unresolved: farther than you can imagine. We have used models, numbers, light time, and mission operations to build a disciplined understanding. Does that mean the distances have finally been imagined? Or does the mind still compress them the moment the model disappears? The answer depends on what imagination is being asked to do. No single representation can preserve visible worlds, true linear spacing, orbital motion, changing viewpoints, and elapsed signal time all at once. But understanding does not require one perfect internal photograph. The final challenge is therefore not to produce a bigger comparison. It is to decide what kind of comprehension science can honestly provide when direct experience is impossible. What does it mean to imagine a distance? If imagination means repeating an accurate number, the problem appears solved. We can state the length of an astronomical unit, list planetary orbital scales, and calculate signal delays. If it means navigating successfully, the solution is even stronger. Spacecraft have reached every major planet, using models that respect those distances. But neither achievement guarantees that the mind forms a faithful inner picture. Human experience offers useful intuition for a room, a street, a city, or a journey across a country. Larger terrestrial distances can be assembled from travel time and maps. Planetary scale is different because direct experience ends long before the numbers do. No person has watched Earth and Neptune remain simultaneously visible at their true relative sizes and separation. Any manageable representation must transform something. This is one reason misconceptions about astronomical scale remain common. Learners can know the correct order of the planets while placing them far too close together. They can recognize that Jupiter is enormous while overlooking how tiny it remains compared with its orbit. Knowledge of individual facts does not automatically produce knowledge of their ratios. The difficulty should not be turned into a universal law about what every brain can or cannot comprehend. Science education research can reveal patterns of misunderstanding and test whether particular representations improve estimates. It cannot establish one absolute boundary beyond which no person can imagine. The responsible claim is narrower. Ordinary intuition and familiar images tend to compress astronomical gaps. Large numbers provide precision, without necessarily providing proportion. A single compact linear picture cannot preserve true separation while keeping every planet visibly detailed. That last limitation is mathematical, not psychological. If Earth is represented by one visible unit, its orbital distance requires many thousands of those units. If the entire planetary system fits on a small screen, an accurately scaled Earth may fall below what the display can resolve. Better concentration cannot give the screen more pixels. The solution is not to search for one perfect image. It is to use several representations, each assigned a clear job. A linear scale model preserves equal distances. It reveals sparsity and the dominance of the gaps. Its weakness is that the planets become nearly invisible and the model stretches across an inconvenient area. A logarithmic map compresses expanding distances in an organized way. It can show the inner and outer planets together while preserving their order and broad ratios. Its weakness is that equal lengths on the page no longer mean equal lengths in space. Light time gives distance a causal meaning. 8 minutes to Earth and hours to Neptune transform kilometers into waiting. Its weakness is that time alone does not show planet size, orbital shape, or the energy required for travel. Mission duration shows what real machines endure. It includes trajectories, alignments, and engineering constraints. Its weakness is that it cannot function as a pure measure of distance, because different missions follow different paths under different requirements. An orbital animation restores motion. It shows why separations change and why launch windows exist. Its weakness is that planet sizes must often be exaggerated, time accelerated, or distances compressed to remain visible. Each model tells the truth by giving up another truth. Understanding grows when the sacrifice is named. This changes the goal of imagination. We do not need to create one internal photograph containing visible planets, exact linear gaps, changing orbital positions, transfer trajectories, and signal delays simultaneously. We need to know which mental tool answers which question. The same principle operates throughout science. An equation may preserve a relationship without resembling the thing it describes. A map may preserve connections while distorting physical shape. A model may isolate one mechanism so it can be understood before other mechanisms return. The solar system becomes comprehensible in layers. First, the crowded portrait is rejected as a spatial map. Then a linear model reveals the gaps. Orbital motion prevents those gaps from becoming fixed roads. Kepler's rule connects the proportions. Parallax and radar explain how the unit was measured. Trajectories show how motion is joined. Light time shows how causality crosses the result. No layer is sufficient alone. Together, they create a structure that can be tested, used, and remembered. There is still an emotional gap between structure and experience. A person can understand that Neptune is roughly 30 astronomical units from the Sun and still feel no internal difference between 4 billion and 5 billion kilometers. That does not erase the understanding. It identifies a limit in the kind of sensation numbers produce. Precision and feeling serve different purposes. Precision lets a mission arrive. Feeling helps us grasp why that arrival matters. The documentary needs both, but they must not be confused. Force should follow the relationships, while the relationships hold whether they feel astonishing. Scale analogies can help, but only if their arithmetic remains consistent. Changing from a grain of sand to a city, then to a highway journey, then to an ocean crossing, may create momentary amazement while leaving no stable model. The comparisons compete instead of accumulating. The 14-centimeter sun model worked because every object and separation obeyed one rule. Its lesson was not that 450 meters feels like 4.5 billion kilometers. Walking through the model distorts speed and effort. Its lesson was the relationship between the tiny worlds and the space around them. The light clock then supplied what the walk could not. Even the fastest possible messenger in established physics needs hours to cross the planetary region. The model and clock answer different questions, and their agreement strengthens both. So the title survives, but with a more careful meaning. Every planet is farther away than the unexamined picture in our minds allows. The distances exceed ordinary experience, defeat compact linear illustration, and remain emotionally resistant, even after their values are learned. But they are not beyond knowledge. They can be measured, modeled, predicted, and crossed. They can be understood relationally without being reproduced as one perfect inner scene. That distinction prevents wonder from becoming surrender. The solar system does not need to shrink before the human mind can understand it. The mind needs a collection of honest tools and the discipline not to confuse any one of them with reality itself. The final picture can now be rebuilt. It will contain less visible detail than the family portrait, but more truth. The planets will become moving islands. The gaps will become light time. The map will become a tested prediction, and the apparent emptiness will become the central fact that connects everything we have learned. Return to the familiar portrait one last time. The Sun and 8 planets stand together, bright, detailed, and close enough to fit inside a single frame. We now know what the image preserves. It shows order, appearance, and difference. We also know what it removes. It removes almost all the distance. An honest linear map cannot keep the same visual richness. Shrink the Sun to 14 centimeters, and Earth becomes a 1 millimeter grain 15 meters away. Neptune becomes a tiny bead roughly 450 meters from the starting point. Pull the camera back far enough to include everything, and the worlds begin to vanish. That disappearance is not an error. It is the central result. The solar system is not primarily a collection of large spheres placed beside one another. It is a moving architecture in which small, widely separated worlds occupy paths around one dominant star. The planets are impressive when approached, but their surrounding gaps govern the system as a whole. Those gaps explain why distance was so difficult to discover. Early astronomers could not view the planetary system from outside. They watched moving lights from the surface of another moving world. Kepler found that orbital periods revealed relative scale. The planets formed one connected pattern before their distances were known in ordinary units. Observers used Earth as a baseline, and geometry as an extension of reach. Mars shifted slightly against the stars. Venus crossed the Sun along paths that differed with viewpoint. Tiny measurements created triangles whose far sides stretched across interplanetary space. Then radar replaced a delicate visual shift with elapsed signal time. A pulse traveled to Venus and returned as a faint echo. The delay measured the gap. The phenomenon that made the solar system seem unreachable became the tool that established its scale. That scale is now precise enough for action. Spacecraft depart Earth, reshape their motion around the Sun, and meet planets years later. Their success confirms more than engineering skill. It confirms that the predicted architecture works. Yet the journey is never simply distance divided by speed. Every planet moves. Every spacecraft begins with Earth's motion. A mission must enter a transfer orbit, meet a future position, and arrive with useful velocity. Nearness in kilometers does not guarantee ease in energy. Even arrival does not eliminate the gap. Commands continue outward at light speed, and observations return after their own delay. A machine near another planet acts before Earth can watch the result. The solar system becomes a network whose links are measured in minutes and hours of waiting. Every planet is farther away than the ordinary picture in our minds suggests. The distances exceed direct human experience. A compact linear image cannot preserve them while keeping the planets visible. Static numbers hide orbital motion. Travel times hide trajectory choices. Close photographs hide the years and emptiness between encounters. But farther than ordinary imagination does not mean beyond understanding. We can hold the scale through several honest tools. A linear model preserves proportion. An orbital map restores motion. Kepler's rule connects the worlds. Parallax reveals geometry. Radar turns time into range. Mission trajectories test prediction. Communication delay gives the gaps causal meaning. Together, these tools provide a testable understanding. The emptiness also requires one final qualification. Interplanetary space is not absolute nothingness. Sunlight crosses it. The solar wind moves through it. Magnetic fields, plasma, dust, radiation, asteroids and comets inhabit it. Gravity connects every region. The system is mostly empty, only in the sense that major worlds occupy very little of its volume. That sparsity is not a failure of nature to fill the frame. It is the frame. Once the gaps are restored, the planets stop looking like beads on a wire. They become isolated moving islands. Earth becomes one small location in a system where light itself needs time to carry news. And still, from that location, humans reconstructed the whole arrangement. They watched patterns, rejected models that failed, measured tiny angles, timed faint echoes, and trusted predictions enough to send machines into the darkness. The solar system never became smaller. Our methods became capable of reaching across it. So the final honest map is not a picture that shows everything clearly. It is a layered understanding of what each picture must leave out. Its worlds are small. Its paths are changing. Its signals are delayed. Its distances are real enough to make a spacecraft wait years, and precise enough to tell that spacecraft where a planet will be. Place the 14-centimeter Sun back at the beginning of the model. Put the grain-sized Earth 15 meters away. Continue outward until Neptune is almost half a kilometer distant. Then imagine a flash leaving the Sun. For minutes, it crosses what appears to be nothing. It reaches Earth and continues. The tiny planets do not move closer for our convenience. The model does not compress. The light travels on, carrying evidence of every meter it crosses. Hours later, it reaches the outer planetary system. The empty-looking distance has become time. And for the first time, the honest map is complete.